Dear friends, welcome to another video pertaining to the gravity method, and we continue to sequentially deepen our understanding and to move to more and more realistic settings. The learning goals of this video are that you fully appreciate how the gravity method integrates over large areas and that this is a curse and a blessing. Please remember the experiment of Cavendish in the first video. And we can turn it into a blessing if we manage to correct for all factors that we are not interested in, and this will be the major topic that we treat in the following. As soon as you unpack your gravimeter and as soon as you start collecting data, you have to realize that although your major motivation will be to map density variability in the subsurface, this is by far not what your primary signal will be at first. There's a whole range of other factors which are typically much larger in magnitude than your target of interest. And we will cover not all, but at least the most important factors. Before we do that, I will briefly introduce the handy coordinate system of spherical coordinates. In spherical coordinates, you can describe a point at the Earth's surface by using the radial distance and the latitudinal angle theta. And both of these quantities are accompanied with vectors pointing into the respective directions. Because we live in a three-dimensional world, we require a third angular vector which corresponds to the longitudinal direction, phi, and in this example, the corresponding vector will be pointing towards you. During the Earth's rotation, this vector will continuously change its direction, and it will do so with the angular velocity omega that is given by the period corresponding to 24 hours. This continuous change of direction corresponds to a continuous acceleration which is oriented perpendicular to the rotation axis. This means in virtually all places on Earth, the detected acceleration does not exclusively depend on the subsurface density, but it also depends on the Earth's rotation. The fact that the Earth is rotating is not overly new, and so we better correct for this effect. And this effect will be largest at the equator, where the distance from the rotation axis is largest, and it will be smallest at the poles, where the distance to the rotation axis is 0. And this is why this type of correction is called latitudinal correction. For a spherical Earth, we can calculate the magnitude of this effect. And unsurprisingly, it depends on the Earth's angular frequency, the Earth's radius, and obviously on the latitude. And you will figure out the details of these equations in the exercises. But what about this section projection here that causes this unintuitive cosine squared? Well, this is related to the fact that the acceleration component due to the Earth's rotation is perpendicular to the rotation axis, but the vertical gravity anomaly detected in your experiment is parallel to the local vertical direction pointing towards the Earth's center, and therefore you need this second projection. So by now, it should be clear that this correction is largest at the equator and smallest at the poles, and I add to this correction is quite significant in magnitude. However, thanks to the Earth's rotation, the Earth in itself is not spherical, but rather ellipsoidal. And this shape can be described with a reference ellipsoid. And knowing this, we now need to go back and check how the latitudinal correction works on an ellipsoid. And here I spare you the mathematical details because those are based on the same ideas but result in a different algebraic expression with the form as written here. The reason why I show this equation is because this is a good moment to define our reference gravitational field, meaning if we assume some mean density of the Earth that causes a mean acceleration as measured by your DIY gravimeter, then we can modify this field with the latitudinal correction and then define this field as our reference field. This is what we would expect at any given location on Earth, assuming that the Earth's interior is homogeneous. And everything that deviates from this expression can be classified as an anomaly, and this is what we are in the end interested in. Okay, this is the latitudinal correction. What's next? It is the dependency on elevation. Imagine that we have collected a nice gravity anomaly profile over a given target with a gravimeter located in an airplane. That is surely possible. At the same time, we also have a ground team surveying the same feature on the ground. And this will result in a different gravity reading. And why? It's because the ground team is closer to the target, and correspondingly it detects a larger anomaly. And this is somewhat confusing because after all, it is the same target. So we should account for this, and we can correct the gravity readings to a common vertical reference level, and typically this reference level is the sea level. And in order to do this, we need to know how the gravitational acceleration changes with elevation, and this comes back to the 1 over r squared dependency that is by now very familiar to us. It represents the entire Earth as a point target. So can we find a simple expression to check how this gravitational field changes near the Earth's surface? And the answer is obviously yes. We can derive such an expression via a Taylor expansion. And this Taylor expansion is centered at the Earth's surface, meaning at the location with the radius RE. So if we evaluate these first terms of this Taylor series, we arrive at the mean acceleration at the Earth's surface. Absolutely no surprises here. And we also find a first order linear correction term which quantifies how the magnitude of the Earth acceleration changes with increasing elevation, meaning with increasing r. And if we plug in the known numbers, we arrive at a correction factor which is approximately 0.3 milligauss per meter. And this doesn't sound like much, but in the world of the gravity method, this is actually quite a lot. It is so much that you should actually record the vertical position of your gravimeter at the centimeter level. And this is not necessarily an easy task. However, once this is done, you can straightforwardly apply this correction of 0.3 milligauss per meter above sea level. And then the next correction will include the surrounding terrain. And to our big disappointment, the Earth is not entirely flat, but occasionally exhibits some topography. And a mountain that is located somewhere in the vicinity of our subsurface target will reduce the gravity reading because of the gravitational pull into this direction. And having a valley nearby doesn't improve things at all, because this will have the same effect just in the opposite direction, because now the landscape over here exerts a net gravitational pull which changes your gravimeter readings on site. And because we're interested in the target and not the surrounding topography, we need to correct for this, and we can do this with a good elevation model of our research area and with a good guess of the surrounding densities involved. So this correction is not hypothesis free. It does require some geologic intuition to be successful. It also requires computers, definitely, because this is a three-dimensional problem that needs to be accounted for. Nevertheless, it surely can be done, and we have reached the next level of maturity unfortunately, just correcting for the surrounding terrain is not quite enough, because there might still be excess material above the reference level, or meaning above sea level, which overlies your target of interest. And this will also offset your results. And so we need to ask ourselves, what is the effect of such a horizontal plate that is situated between us and our target? And this we can answer with the theory from the previous video, and we called this the Bouguer plate solution. And it results from this triple integration. And the correction, I would say, is surprisingly simple. It is over here. It only contains the thickness of the slab and its mean density. So similar to the terrain correction, we need to make some assumptions about the density, and therefore this step is also not hypothesis free. But what we retain from this is that as soon as we subtract the effect of the Bouguer plate, we visualize gravity anomalies which are situated below the reference level, or more specifically below sea level. Phew, this is a long video, 2 more to go. As it turns out, even if you place your gravimeter at a given location and you don't move it at all, it will still provide different readings because of tidal effects. Tides on Earth emerge essentially from the Moon and from a joint Earth-Moon rotation. So let's consider this two-body system and now visualize that the gravitational pull of the Moon exerted onto the Earth will be larger on the near side than on the far side. And this is again because of the 1/r² dependency. And such a gradient is the origin of tidal deformation, and it will pull the oceans towards the Moon. Importantly, there is a second effect that plays a role here. Earth and Moon rotate together around a common axis, and similar to the latitudinal correction, this induces a net acceleration, which again matters. In fact, we can decompose these two components into two components, one into a radial direction oriented towards the Earth's center, and one into a parallel direction. And this joint effect then results in a lunar gravity field. Now the Moon is over here. In a lunar gravity field that has 2 bulges, one towards the near side and one towards the far side, which originates from this rotation. And I mention this here because there is quite a bit of conceptual confusion about the origin of tides, and please remember that the Earth's rotation around its own axis has no role for the formation of tides. In terms of the gravity data corrections, tidal effects can be corrected for either by using a tide model, including those effects, or by referring to a reference gravimeter station, and I will show you a record of one. And those reference stations, they are able to monitor tidal effects. The units here are microgal, so this is quite a bit smaller than what we have seen for the elevation correction, but nevertheless, it also matters. The next correction pertains to the instrument characteristics. Imagine you collected a dataset once again in a profile ranging from A to F, and at that end of the day, you return to location A and you take another reading. To your big surprise, this reading is different even after a tidal correction. And this is possible because your instrument has many sensitivities and may drift, for example, with temperature. And with such a repeat measurement, you at least notice this effect, and you can probably also correct for it to a certain extent. And after all of this is done, only then can you really start to interpret your gravity anomaly as a function of the density variability in the subsurface. And all of those corrections are additive. And sometimes Gravity products are presented with different levels of corrections applied because they pertain to different scientific questions. So most of them contain all corrections up to the terrain correction, and then this product is referred to as the free air anomaly, mostly because it has been referenced to the same vertical reference level, removing the dependency of the sensor elevation. If the Bouguer plate correction is also added, then the gravity anomalies are referred to as the Bouguer anomalies, and those image structure beneath sea level. But remember, none of those products are hypothesis-free, but they nevertheless offer a lot of insight into the internal structures of the Earth. So now let us summarize this rant through many different corrections. They are all needed because the gravity method integrates over many processes and most of them are of no interest to you. Therefore, we require a lot of data reduction. And in that data reduction, we have learned a few things on the side. We have learned that the Earth is best described with an ellipsoid due to the flattening as a function of the rotation. And we have also learned the mechanism, the two principal mechanisms of tides on Earth. And then we realized that there are different levels of representing gravity data. There's a representation as a free air anomaly, and there's a representation of a Bouguer anomaly, and there are other representations, and we will discuss those in the exercises, and also I will provide you some maps which you can interpret. We are still not at the end of the gravity method. We will still have to explore different gravimeter types, and we also have to properly define the geoid, the reference level that I was often referring to, and this will be part of another video. Thanks for listening, enjoy your break, and bye-bye.